have Mr. Prasanna Srinivasan, Global Market and BD Manager, Parker Hannifin, and he shall be sharing his deep insights on Encapsulant foams for thermal runaway mitigation, lightweighting, and mechanical dampening. May I please request Mr. Srinivasan to please be on the dais. Also, I would like to request Mr. Aloysius Daniel Gandhi to please share his presentation with the backend team so that we can quickly take it forward. Over to you, Mr. Srinivasan.
Hello everyone, my name is Prasanna Srinivasan. I'm part of Parker Hannifin based in our headquarters in the US. I'm going to talk a little bit about, I think, a very topical subject in the world of batteries today, which is thermal management, particularly as it relates to battery safety. And I'll talk about some of the solutions that we have to offer in this market. So this is a rough overview. I got a lot of slides, but feel free to come by our booth, which is at the beginning of this hall, if you want to have further discussions, have any questions, want to learn about our products some more. But I'll talk about a quick overview of our company, talk a little bit about why safety is critical in the world of EVs, a little bit about our solutions in the world of EVs as it relates to safety, and then I'll go through a quick case study that we did with some of the encapsulants and foams that we have. Parker, big company, a lot of people, you can Google us, but more interestingly, come and talk to us at Hall 14, 11. So everything we do is pretty much custom solutions. So we basically come in, work with module and pack assemblers, and we basically develop thermal solutions, safety solutions specifically for your design constraints. The earlier you get us involved, the better off you will be as you go through your design process. So we work all across the EV world. We are the largest supplier of materials in the world of thermal management as it relates to automotive. But of course now, the market has branched out much further beyond automotive, right? So automotive was the leading end of this whole EV wave. Certainly in India, e-scooters are a big deal. But we've also seen the electrification really spread into the industrial side. So, we have a lot of market interest in the world of aerospace, in buses, trains, transportations, material handling trucks, things, recreation vehicles, etc. So it's really much more than just automotive. But what we do within the battery pack itself is, we have a whole bunch of solutions. I'll talk about, a little bit about all of these and how it relates to safety. We have solutions relating to power electronics. We have solutions related to motors. But we also have solutions in the world of, as it relates to sealants, O-rings, EMI shielding. So, Parker is a really large company with a very diverse portfolio, and, we'll be happy to talk about all of that. So really digging into the subject for today, right? So why is safety critical in the world of EVs? There's really three different aspects of safety to consider. There's this thermal aspect, right, where you have cells, irrespective of the form factor, the cells start to heat up. That really leads to issues with respect to a fire, thermal propagation, etc. So that's one aspect. There is this electrical component to it where you have a shorting, over voltage, over current, that leads to, thermal issues ultimately. And then the last one is related to environmental conditions, right? So you potentially have, a debris, nail penetration, potential issues with water, ingress, etc., etc. So all of that is really, what safety means, right? So people typically think of thermal, but it's much more than that, right? And we have solutions in all three areas. But why is safety important? I mean, this is a really small battery pack that sits in an e-scooter, and you can see the explosive energy, right? I mean, that's really, showcases why safety is a big deal. And, the market has actually gotten pretty smart in terms of trying to figure out what to do with safeties. I mean, regulations are a big deal, right? So, 3-4 years ago, I apologize for some of the formatting here. It doesn't seem to show well. But, about 4 years ago, regulations were very, very nascent. People are talking about it, not a lot going on. And then once China started moving in, the rest of the world sort of followed, right? So initially it was about making sure that you have enough time for occupants to evacuate vehicles, right? So there was this 5-minute evacuation requirement that China first, propagated. And then, the market moved on to much more than that, right? So in India, for example, AIS 156 is a big deal. The UL requirements are certainly starting to come in. UL 2496 test, basically has very specific requirements on how to handle certain, FR conditions, right? So regulations are a big deal. It's moving in a good direction. There's very little convergence. Hopefully in the next 5 to 6 years, you would expect, to be a much more, convergent effort where, globally you have a singular standard that, designers will work towards. In terms of our solutions, trying to move forward. Okay. So we have a whole slew of solutions. So the first one is dielectric coatings. Whether it's corrosion prevention, whether it's to prevent, electrical shorting and to provide electrical isolation. We have dielectric coating solutions. The second big one is really thermally conductive gap fillers, right? So as the batteries operate, particularly in the world of fast charging, it's critical to get the heat out. If you don't get the heat out, you'll have isolated hotspots, which ultimately will lead to thermal issues. We have a whole bunch of thermally conductive gap filler solutions that basically get the heat out of your cylindrical, prismatic, and pouch cells. You have structural adhesives that provide mechanical, sort of rigidity. Sometimes it doubles up as a thermally conductive material, but basically helps with, assembly of the battery pack. That also helps with environmental conditions, right? So, whether it's adhesives or sealants, you have materials that are IP67 rated that helps prevent water from ingressing and causing damage into your battery packs. And then the last one, which I'll talk about a little bit more, is encapsulant solutions. We have both foam solutions, which are low density solutions, as well as thermally conductive potting materials or encapsulants that basically help with, preventing a thermal propagation or thermal runaway kind of situation. So this whole concept of thermal propagation, right? So there is a lot of interest in foams, particularly in the India market. And the reason is pretty simple. If you have a cylindrical cell design, you have two cells. Typically you have, I'll see if this pointer works. You typically will have a thermal interface material at the bottom. That's, as the cell heats up, you want the heat to be wicked away or removed through the gap filler. But the problem is you have air gaps between the cells, and that, basically provides a convection pathway, right? So if one cell basically becomes hot, due to convection, the neighboring cells heat up. If you actually have an encapsulant material in between, now there are two kinds of encapsulant materials. There is this low density foam. What that does is that it has bubbles, air pockets, and so the convection is really limited within those bubbles or air pockets, right? And that prevents the heat from actually spreading. The other one is you have a potting material, which is thermally conductive, and purely by virtue of thermal mass, that can actually help the heat from, basically spreading easily to a neighboring cell to a point where you actually have a thermal runaway situation, right? So the best analogy I have is, you have a double pane window, right? So you have air in between. So you have, exterior environmental conditions, heat, cold. The double pane window actually prevents the interior from, basically seeing the same environmental effect, right? So that's basically the concept of using foams. Now you add some flame retardant properties to the foams, all of a sudden, your foams become much more potent, right? So those are two different kinds of, encapsulants, a thermally conductive encapsulant and sort of a thermally insulative encapsulant. Both of them have been proven to be incredibly effective in terms of thermal propagation. And so the case study I have to show is really, the first one is encapsulated with a thermally conductive material called Se309, which is a silicone. And so what we did is we basically did a cluster level testing where we had a cylindrical cell design, a center cell, which actually had a heating mat. And then you had around 18 or 18 other cells all around it with thermocouples everywhere to measure the temperature, to measure the voltage. So this is our control sample. And then on the actual test sample, we actually encapsulated this entire area with our silicone material. And the property of the silicone material is listed here. It's a V0 rated material with a thermal conductivity of 1 watt per meter Kelvin. And so we basically wanted to see how this encapsulation would help with the thermal runaway prevention, right? And this is an actual video that we sped up. You can actually mute the volume if you want. So this is the control sample, like I said. The center cell is initiated, thermal runaway is initiated by heating it up, and then your surrounding cells are connected with all kinds of measurement devices, right? And then you basically use an encapsulant on the entire component. So the control, both of them actually are entering into thermal runaway. The center cell is, right? Both of them actually have some explosive, reaction, right? On the left, you're going to see a continued reaction happening where there is actual thermal propagation, right? One cell after the other goes, a lot of energy being released. On the right, there's really nothing, right? So eventually, the cell extinguishes, right? So the first reaction, obviously, that is to be expected. That's the electrolyte leaking. That's basically the electrolyte combusting, catching fire, right? But eventually, in just about a minute, it is extinguished fully. Here, this one just keeps going and going and going till all 19 cells basically enter into runaway. And even more sort of, impactful is really what you see afterwards, right? So you have cells scattered everywhere, whereas in the case of, encapsulant, right? So you actually cut it open, you actually see the cells intact, right? Neighboring cells actually quite intact. So very powerful video, but if you think about your electric scooter or automotive, right, that has a design like this, this could actually be a very cheap solution that could help you with meeting your AIS-156 and basically preventing thermal propagation. And this is some data that I'll share. So basically on the y-axis is the time and the x-axis is the temperature. The red cell is actually the initiator cell. So this is the control sample, right? So where you don't have any encapsulant in between. So what you see is after about 5 or 6 minutes of heating, using the resistive heating element, the first cell actually enters into thermal runaway. You see a very high temperature spike, right, 600 degrees. And then the neighboring cell, one cell after another, basically spikes in temperature, reaching 1000 to 1200 degrees C, right? And you basically have all of these cells enter into thermal runaway. And that's really what is thermal propagation, right? So you have an initiator cell, and then that propagates to neighboring cells. In the case where you actually have an encapsulant, you do have the first cell go into runaway. But the interesting thing is you look at the time, right? So the first one goes into runaway in the control sample. It goes into runaway about 5 minutes in. Here, it takes a good bit of time before even the initiator cell goes into the runaway. And the reason for that is pretty simple, right? You have a huge thermal mass for the encapsulant material that's going to get the heat out. And once the heat is removed, it takes a lot longer for even the initiator cell to go into runaway. And of course, the neighboring cells, they all stay below the 100 degree, 120 degree mark, right? Which is really the ideal scenario. So pretty straightforward, case in terms of why you need some kind of solution to prevent thermal runaway. The second sort of solution is really foams, right? So the cylindrical cell design in general has gone seen a big change where you had air gaps in between with a gap filler to now having some kind of foam solution or encapsulant like I talked about. There are really two different kinds of foams that we are working on. The first one is what we call the top cell foam. So you have cylindrical cell with electronics in the top that you might want to protect. You might actually have a foam solution on the top. You could also have an intracell foam similar to the SE309 example. So I'll talk about that in a little bit more as well, where you fill the entire area with a very low density foam. The interesting thing about this foam is you can actually make it multifunctional, right? So you can actually have some structural component to it. You can make the foam flexible. You can make the foam rigid. That in turn provides mechanical dampening that could provide structural rigidity. So you can really add a lot of functionality beyond just helping solve thermal runaway problem, right? And this is some of the examples of some of what I'm talking about. So you can make it super flexible, you can make it somewhat flexible, you can make it very rigid. Each of that will will determine its own property set, right? So I'll speed through this. I'm running out of time. There are also two other types of foams, if you will, right? So first one is an expanding foam. So this looks like a foam that foams up, right? So you think about any foam, you think about a material that foams up, and you have air pockets in between. Or you could have a syntactic foam which actually has glass bubbles that doesn't expand, but actually has glass bubbles already embedded in it. And each of them has their own advantages, right? So I'll skip through this in the interest of time. I just want to show this video on, it's a pretty similar video as the 309. If you can play the video. Should play, okay. The story is pretty simple. It's a super low density, density of about 0.2 grams per cc. And very similar setup, right? You have the control sample, which is surrounded by cells. This is what we call cluster level testing. And you have an expandable foam that flows really easily between gaps of 1 to 2 millimeters. It's a V0 rated material once again, right? So story is very simple, right? So you have a super low density material that really does not, beyond the first cell firing, there's really very little that happens, right? So this material is thermally insulative, whereas the first video I showed is a thermally conductive material. This one just keeps going and going and going. And this one, in about a minute, basically will self-extinguish. Right? And of course, this initial burning, right, that's to be expected. That's again the electrolyte leaking out and catching fire. But there's really no explosion beyond that, right? So the interest of time, I'll skip ahead. Very similar story, right? Initiator, in the case of the foam, the initiator cell goes, nothing else does. We also measure the voltages, right? So in the control sample, you have a bunch of cells where the voltages drop. That's basically that's what you would expect when you actually have a thermal runaway situation, right? Whereas when you have an encapsulant here, only the initiator cell drops, and the rest of the cells still have the original voltage of about, I think in this case 4 volts still intact. Again, the control case, you see some of these cells ejected, stuff strewn all over the test bench. The interesting thing with this urethane foam is the cell will actually vent through the foam. So the gases that come out of the cells that actually can very easily escape through the vent, to the environment, right? So you actually don't pack those gases into your battery housing, which is a pretty big deal. I'll skip through this. So just the key takeaways, safety is a big deal. I think everybody here knows that, otherwise you wouldn't be sitting here. We have a lot of solutions that we would love to talk about, in particular foams and encapsulant materials. These materials are extremely multifunctional, right? So, come and talk to us about what sort of design requirements you have, and we'd be happy to assist you. With that, thank you for your time.
Thank you so much, Mr. Srinivasan, for sparing your time and sharing the deep insights on the presentation and to our audience. May I please take the privilege and honor to share a token of appreciation to Mr. Srinivasan on behalf of Informa Markets India.